Hey everybody, welcome to lesson 2.4, Intro to Logarithms. So this is to be completed with your 1.5.2/1.5.3 sections of your cognitive textbook, but I also thought I would make this video to kind of help you out through it. Our EQ, what is the purpose of a logarithm, and then how do you interpret log of b and ln of b? Okay, so first, this section is going to be on cognitive section 1.5.2. Logarithms are an important operation to be performed in advanced algebra. What they allow us to do is find the value of a variable when it is in the exponent. So, for example, we have this question, 5 to the x equals 26. Find x. Well, we know with algebra we're supposed to do inverse operations in order to find variables, right? That's how we isolate them, is by doing inverse operations. But what's the inverse of something that's in an exponent? That I don't really know. But here's what I do know. There is a number x that satisfies this equation. We just don't know it off the top of our heads. We need some pretty fancy calculator action for that, and that's where the logarithm comes in. In essence, logarithms are the inverse operations of exponents. You see, what logarithms allow you to do is use notation to answer the question, what power should I raise 5 to in order to get 26? That's what this question is going to ask, and we use a logarithm to do that. So, the numbers that you enter into a logarithm are log base a of b equals x. That's how you read this statement. Log base a of b equals x, where a is the base, b is the argument, and x is going to be your answer. So the purpose of a logarithm is to rewrite an exponential equation such that we can work with it. So exponential equations in the form of a to the x equal b are equivalent to the expression log base a of b equals x. These are equivalent statements, so long as we have a being greater than 0, b being greater than 0, and that a does not equal 1. Now, still, these seem to be kind of a mystery. Well, let's actually use a calculator to evaluate some logarithms, and let's try and work with that. You're almost always going to need a calculator to work with logarithms. So logarithms can be evaluated with a calculator. There's also these old school logarithm tables that you can work with and you can use as a reference. People have already done the hard work for you. You just have to look at them. But in the 21st century, all we end up using is calculator. Alright, so if you follow the link, you'll find a logarithm calculator that you can use. Now, pretty much any scientific calculator is going to have this. If you have a graphing calculator, you may even be able to do more advanced logarithms too. But let's go ahead and take a look at this example. Log base 10 of 0.01. We read that as log base 10 of 0.01 equals what? Well, let's use our calculator to do that. We are asking ourselves 10 to the what power equals 0.01. When we calculate it, we see -2. So what that tells me is that 10 to the -2 power equals 0.01. So 10 to the -2 power equals 0.01. Hence, solve for x in 10 to the x equals 0.01. So now what we can end up doing with this question is saying, all right, 10 to the what power equals 0.01. Now it's just a matching game. X is -2. So x equals -2. And now you've done some pretty advanced algebra. So now let's go ahead and take a look at a few other examples. This is just like the mechanics of working with logarithms and making sure you understand it. Now, this was always a struggle for me, and this was the easiest way for me to work back and forth with logarithms and exponential equations because we need to do that quite a bit. So let's go ahead and take a look at this example. We want to rewrite in the form of a logarithmic expression, log base a of b equals x. Well, if this is log base a of b equals x, remember x is going to be the exponent. So a to the x equals b. A to the x equals b. And actually circling my base, drawing this arrow to the x, and then drawing this other circular arrow to the b is what helps me answer this question. Okay, so we are going to do the same thing here, noticing that the base of my exponent is going to be the base of my logarithm. Okay, so I have log base what? Well, the base of my exponential is the base of my logarithm, 4, and now my exponent is what goes on the other side. That's my equal sign. Equals 3, and then what goes into the middle? 64. And this is kind of my process that I go through it, but what I always have to do is just double check. 4 to the third equals 64. And that shows me that, yes, that's indeed the way I read this expression, and that means I got it right. So this one is log base 4 of 64 equals 3. You can also go back to a calculator to double check your work. So we'll do the next one the same way. We'll try and go a little bit faster. So I have log base 10 of x equals 27 of x equals 27. So it's a little bit of a back and forth. I double check my work. 10 to the x equals 27. I've got it right. Go ahead and check your work on this next one, 5.3 to the negative 2.4 equals 0.0183. We don't care how gross the numbers are. Just go ahead and write it as a logarithmic expression. Now, let's go ahead and do another couple of examples. Rewrite in the form of a to the x equals b. Now, for me, this is a little bit easier because, again, I have that circle and circle arrows method down pretty cold. So log base 5 of 8 equals 1.29. That tells me that 5 to the 1.29 equals 8. And I just have to rewrite what I say in my head. 5 to the 1.29 power equals 8. And it's that simple. Again, this is something that you can check in your calculator. 5 to the 1.29 power, does that indeed give me 8? If you get the right answer, you know you wrote it the correct way. Next example. Log base 81 of 3 equals 1/4. 81 to the 1/4 equals 3. And there it is. Do the same thing with question number 3. Do this one on your own. Alright, moving on to the next page, we've got some special logarithms, and this is where we are going to start to get into section 1.5.3. But at the very end of section 1.5.2, we talked about special logarithms, and that's the common log. So if you see log b, seems like there's a problem. There's no base. Well, very similar to where we had the square root had an index of 2, but we don't actually write that index because it happens so common. We actually have this thing called the common log, and the common log is where we use base 10. So if you see log of b, there seems to be no base. You should interpret it as log base 10 of b. Okay? So if we had log of 5 equals x, then what this expression is actually equivalent to is 10 to the x equals 5. My base, even though I don't see it, I know it is 10. Okay? Now, the other special one, this is where we get into 1.5.3 in cognitive, is the natural log. This is log base e. E is known as Euler's number. You You might also hear pronounced as Euler or Euler. He's a Swiss guy. A Swiss physicist and mathematician, huge in the world of mathematics, super important, and is credited, maybe unfairly credited, with this thing called the natural number, and we kind of reference him with that base E. Okay, so Euler's number, super important. You can see this cognitive video on where it comes up, but it's a number that is similar to pi, that is irrational and goes on and on and on forever. So we know as pi is 3.1415927 blah 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 blah. E is a similar and just as important number in the world of mathematics, and it's 2.71828, on and on and on. It doesn't ever repeat. Okay, so important, and it has tons of practical applications, especially with logarithms, because E is a very common base in exponential equations. Okay, we can model bacterial growth, any kind of population growth. We can model the way that money can start to accumulate interest in a bank account or in some kind of investment using continuous growth by using this number base E. So this is a super important number, and it's found in nature, in naturally occurring phenomenon all the time. It can be a really, really good model, so we like this number E. We say that e to the x can be rewritten as log base E of B. The thing is, we don't ever use this. What we do, instead of log base E of B, we will say ln of B. Okay, and this is, again, the letter ln, so we pronounced it as ln of B. Okay, so why is it ln? Why not NL for natural logarithm? Well, again, Euler was a Swiss mathematician and physicist, but in a lot of Europe at his time, France was a predominant power. Thus, French was the predominant language. Okay, it was just a very widely spoken thing, and so we think of this as log naturel because it's all Frenchy. So ln for log naturel, ln became the common way of expressing this thing. So that's why we use ln of B instead of NL. Okay, now we want to rewrite the following as a logarithmic expression in the form ln of B equals x. Well, we do the same exact thing, right? E to the 5 of 148, or e to the 5th power, is approximately 148. That's the same thing as saying ln of 148 equals 5, or is approximately 5. And you can double check this with the calculator, but again, remember, your exponent usually is your answer. Exponent is your answer in a logarithmic expression. So again, if we think about it in that way, we would say for the next one, ln of blank equals blank. Well, again, my exponent, I want to think about that as my answer. So ln of blank is approximately m. We can say ln of w is going to be approximately m. But whenever we're working with expressions such as this, we can just say it's actually equal to, because we are not relying ourselves on any rounding errors or anything like that. So ln of w equals m. And one way I can think about this is if I were to rewrite this, just to check my work, log base E of w equals m, I can double check myself and make sure I did it the right way. E to the m equals w, and that does check. Okay, now let's go ahead and take a look, go in the other direction, and then I'll ask you to answer these last few remaining questions. Rewrite the following as exponential expressions in the form of e to the x is approximately b. Well, again, we know that the base is e. E to the c equals 2. E to the c equals 2. Again, just follow that process, circle your base, say it out loud. I can't tell you how much talking mathematics will help. I'll leave you to do that next one. ln of 5, this is something that you can evaluate on the same calculator website. You'll be able to notice there's a drop-down menu for you to change to a different kind of base. Okay? Let's go ahead and take a look at number 4 together, and let's see how we can actually answer these kinds of questions utilizing a logarithm. So, given that e to the x equals 25, we want to find the value of x. Again, this is a common thing that we use logarithms to find the value of an exponent. So, let's go ahead and write this out as an expression of a logarithm, ln, and if you want to, you can start by doing this, log of e of 25 equals x, because again, I know my exponent should be my answer. Now rewrite it in the common form, ln of 25 equals x. Well, look at this. That's calculator. That is something that I can punch into my calculator. If I happen to find that other calculator website, I can change my base to e of 25, calculate it, and we get our answer, 3.2188758. Whenever you're writing out answers like this where you're evaluating something, go ahead and write them out. 3.21885. Use your ... And then what you want to do is round this to 3 significant figures. We'll talk a lot more about significant figures as the course goes on, but we will say that x is going to be approximately 3.22. And that is our answer, rounded to 3 sig figs. And that's it. Good luck on your assignment in Cognity. Hope this helped. Have a wonderful day.